The mountain is moving. Deep beneath one of America's most closely watched volcanoes, the ground is trembling with a restless rhythm. Small earthquakes rippling through the rock, the surface subtly rising and falling, and enormous forces shifting where no human eye can see. Nothing is exploding. There is no towering ash cloud above the summit, and yet something is happening beneath the mountain that scientists cannot afford to ignore, because volcanoes rarely announce their most important changes with one dramatic event. More often, they whisper first, a tremor, then another, a slow deformation of the ground, a change in the way underground fluids move. Individually, these signals can look almost meaningless. Together, they can reveal that an enormous geological system is becoming more active, and that is what makes Mount St. Helens so fascinating. The volcano in Washington state is one of the most dangerous volcanoes in the United States, not because it is constantly erupting, but because its history has proven just how violently it can transform. In 1980, an entire mountainside collapsed. Within moments, the landscape changed forever. But today, scientists are not simply watching the summit, they are listening to the mountain from below, and what they hear tells a much deeper story about how volcanoes awaken, how magma moves through Earth's crust, and why a volcano can remain quiet for decades while still being very much alive. Almost nobody sees these changes happening. That is because the most important part of a volcano is hidden. The dramatic cone that rises above the forest is only the visible tip of a system extending kilometers beneath the surface. And down there, rock is not always as solid and motionless as it appears. It can crack, it can deform, it can melt, and sometimes it can begin making room for something that has been trapped beneath the earth for thousands of years. So what exactly does all this shaking mean? Is Mount St. Helens actually getting worse? Or are these earthquakes simply the normal breathing of a sleeping volcano? To understand that, we have to go back. If you enjoy evidence-based science stories that turn strange discoveries into understandable mysteries, subscribe and stay with us. Because this story begins long before modern instruments ever detected the first tremor. Mount St. Helens is part of the Cascade Range, a chain of volcanoes stretching from northern California through Oregon and Washington into British Columbia. The mountains exist because one enormous tectonic plate is being forced beneath another. Far below the Pacific Northwest, the Juan de Fuca plate is descending beneath the North American plate. This process is called subduction. Scientific fact, when one tectonic plate sinks beneath another, water and other materials carried downward can help trigger melting in the mantle. In plain English, the descending plate changes the chemistry deep underground, allowing some of the surrounding rock to melt. Think of it like adding a powerful ingredient to a pressure cooker. The system was already hot and active, but the added material changes what happens inside. Why does that matter? Because the molten rock produced deep underground does not necessarily stay there. Magma can rise. Some of it cools inside the crust. Some accumulates in underground reservoirs, and some eventually reaches the surface. Over geological time, repeated eruptions build volcanoes. Mount St. Helens is one of the products of this enormous process. But its most famous chapter came in the 20th century. On March 20th, 1980, a magnitude 4.2 earthquake struck beneath Mount St. Helens. It was the beginning. Within days, hundreds of earthquakes were being detected. Then thousands. The mountain began to change. Imagine standing near the volcano during those weeks. The summit would look familiar. The forests would still surround the mountain. Snow would still cover the slopes. But instruments were detecting something extraordinary. The northern side of the volcano was beginning to bulge outward. The surface was moving, and it was moving rapidly. Scientific fact, before the May 18, 1980 eruption, the north flank of Mount St. Helens expanded dramatically as magma intruded into the volcano. In plain English, magma was forcing its way upward and outward inside the mountain, pushing the surrounding rock aside. Imagine inflating a balloon underneath a blanket. You might not see what is happening inside the balloon, but the blanket begins to rise. The mountain was doing something similar, except the material pushing outward was molten rock under enormous pressure, and then came the catastrophic collapse. On May 18th, a massive landslide swept away the northern flank. The collapse suddenly released pressure on the magma system. The result was one of the most powerful volcanic eruptions in American history. The blast devastated more than 500 square kilometers of surrounding land. Forests were flattened, rivers were transformed, the summit was reduced by hundreds of meters. A mountain that had existed for thousands of years had been radically reshaped in minutes. But this is where the story becomes even more interesting, because Mount St. Helens did not die. It continued to evolve. After the 1980 eruption, scientists watched the volcano rebuild. Lava emerged. A new lava dome formed inside the enormous crater. Then the dome grew. It collapsed. It grew again and again. The volcano was no longer simply a mountain. It was a dynamic geological machine. Picture this. Deep beneath the crater, magma slowly rises. It enters the upper crust. Pressure changes, gas expands, rock cracks. Tiny earthquakes travel through the mountain. The surface responds. Then the system settles. This is why earthquake activity around a volcano is so important. Earthquakes are not automatically evidence that an eruption is coming. That distinction matters. Scientific fact: volcanoes can produce seismic activity for many different reasons, including magma movement, changes in underground fluids, pressure adjustments, and the breaking of rock. In plain English, a shaking volcano does not necessarily mean magma is about to burst through the surface. Think about a house settling. A creak does not mean the building is collapsing. But if the creaks suddenly become louder, more frequent, and happen alongside visible movement in the walls, you pay attention. Scientists do the same thing with volcanoes. They don't watch one signal, they watch the pattern. That is where modern monitoring becomes extraordinary. Today, volcanoes like Mount St. Helens are surrounded by networks of seismometers, GPS stations, cameras, gas sensors, and other instruments. These devices allow scientists to detect movements that would be invisible to people standing on the mountain. A GPS station can measure tiny changes in the position of the ground. A seismometer can detect earthquakes far too small for humans to feel. Gas instruments can reveal changes in volcanic emissions. Together, these measurements create something like a medical examination for an entire mountain. And that comparison is surprisingly accurate. A doctor rarely diagnoses a patient from one heartbeat. They look at temperature, blood pressure, blood chemistry, imaging, symptoms, and changes over time. Volcano scientists work in much the same way. They build a picture. Then they ask whether that picture is changing. And this brings us to the phrase that makes headlines so compelling: the volcano is shaking. It sounds terrifying, but scientifically the real question is not whether Mount St. Helens is shaking. It is whether the character of that shaking is changing in a way that indicates magma is moving toward the surface. That is much harder to determine. And this is where scientists have learned one of the most important lessons from Mount St. Helens. Volcanic systems do not behave like simple countdown clocks. There is no universal sequence that says earthquake number 1 will always be followed by eruption number 2. Nature is messier. Magma can move and stop. Pressure can build and release. Earthquakes can increase without an eruption, and volcanic systems can remain quiet for long periods before suddenly becoming active again. Think about a pot of water heating on a stove. Sometimes bubbles rise steadily. Sometimes they disappear. Sometimes the water seems calm just before boiling begins. The surface alone does not tell you everything happening at the bottom. A volcano is vastly more complicated. Now zoom out. What happened at Mount St. Helens changed volcanology. The 1980 eruption became one of the most intensely studied volcanic events in modern American history. Scientists were able to compare what happened before, during, and after a major eruption. They learned how earthquakes developed. They tracked deformation. They studied the landslide. They measured the eruption column, and they watched the volcano rebuild itself afterward. Every stage became data. Every earthquake became another clue. Every deformation measurement became another piece of evidence. And that knowledge now helps scientists monitor other dangerous volcanoes across the United States. From Mount Rainier to Mount Hood, from Mount Shasta to Lassen Peak, the lesson is larger than one mountain. A volcano can be quiet without being dead, and active without erupting. That distinction is crucial, because the real danger is not necessarily constant activity, it is uncertainty. Mount St. Helens has shown scientists that a volcano can move from subtle unrest to catastrophic eruption, with consequences that extend far beyond the summit. Now imagine what modern monitoring would see if a major change began tomorrow. First, perhaps a swarm of earthquakes. Then changes in their depth and location. Perhaps the ground begins deforming. Gas emissions might change. Thermal activity could increase. Different signals would begin appearing across the monitoring network. No single observation would necessarily prove an eruption was coming, but together they could tell scientists that the system was changing. And that is exactly why scientists continue watching, not because every earthquake means disaster, but because patterns matter. Today, Mount St. Helens remains an active volcano monitored by scientists as part of the broader effort to understand volcanic hazards in the Pacific Northwest. Its crater still contains the scars of the 1980 catastrophe. Its lava dome remains a reminder that the volcanic system never simply disappeared. And beneath all of it, the same tectonic forces continue operating. The Juan de Fuca plate continues its slow descent. The mantle continues moving. Heat continues rising. Rock continues changing. The mountain may appear motionless from a highway hundreds of kilometers away. But geologically, it is anything but still. Think about what that really means. The landscape around you can look permanent. Mountains appear eternal. Rivers seem ancient. Cliffs feel immovable. Yet Earth's surface is constantly being reshaped by forces operating on timescales far beyond a human lifetime. Mount St. Helens simply gives us a rare opportunity to see those forces in action. The shaking is not necessarily a warning siren, it is a message. A tiny vibration traveling through solid rock, a signal that something underground is adjusting, and scientists are learning how to listen. That may be the most remarkable part of the story. Human beings cannot see deep inside a volcano. We cannot simply cut the mountain open and inspect its magma chambers. Instead, we listen to earthquakes. We measure movement. We analyze gases. We watch thermal changes. We combine thousands of observations and reconstruct what may be happening kilometers beneath our feet. In other words, we are learning to see the invisible. And there are still unanswered questions. How exactly does magma move through fractured crust? Why do some periods of unrest lead to eruptions while others fade away? How quickly can a volcanic system transition from one state to another? And can scientists ever predict eruptions with enough precision to know exactly when and where the danger will occur? For now, the answer is no. But every eruption teaches us something. Every earthquake adds another measurement. Every monitoring station becomes another set of eyes. And every generation of scientists gets a little better at understanding these enormous systems. So when you hear that one of America's most dangerous volcanoes is shaking, don't imagine a simple countdown to catastrophe. Imagine something more complicated. Deep underground, an ancient geological engine is still operating. Rock is breaking. Pressure is shifting. Heat is moving. And scientists are listening for patterns hidden inside the noise. Mount St. Helens reminds us that Earth is not a finished landscape. It is alive with motion. The mountains are still being built. The crust is still moving. The planet is still changing beneath our feet. And sometimes, if we listen carefully enough, the Earth tells us, not with words, with a tremor, a vibration, a signal traveling through stone from a world we cannot see. That is why Mount St. Helens matters, not because every earthquake means an eruption is coming, but because this mountain has shown humanity, in the most dramatic way imaginable, just how powerful the hidden Earth can be. And perhaps that is the real mystery. We spend our lives looking toward the stars, searching for worlds beyond our own. Yet beneath our feet is another universe, hot, pressurized, restless, and still largely hidden from us. Mount St. Helens gives us a window into that world, and as long as its instruments continue recording every subtle movement, scientists will keep watching. Because the next great discovery may not come from a distant planet. It may come from a vibration traveling through a mountain in Washington. If you want more evidence-based science documentaries that uncover the hidden forces shaping our planet and the universe, subscribe and join us for the next journey.